Start the session. The first speaker is Asu, and she's talking about near potential games.
Thank you very much. Thanks for the invitation to this very interesting workshop. So I'll be talking about our recent work on convergence of different classes of adaptive dynamics in near potential games. And by that, thank you. And by that I mean games that are close in some sense that I'm going to formalize in a second to the set of potential games. In particular, I'm going to present results about limiting behavior of such dynamics being contained in small epsilon equilibrium sets for these games. This is joint work with our student Ozan Kandogan and Pablo Parillo from Leeds, MIT. So let me start by actually showing that this phenomenon that I told you about, the fact that when you have two close games, the limiting dynamics is close, need not be true in general games. So let's pick up this very simple example. So we have two games, and you can see that the only difference between these two games is the payoff for the role player for playing strategy profile BB. So we have that that payoff is different by 2 theta. And we're going to see that these have actually, this difference in payoffs, this small difference in payoffs may have significantly may lead to significantly different limiting dynamics. So in the first game, if you try to look at the Nash equilibria, the unique Nash equilibrium of this game is a pure strategy profile, BB, and that's not too hard to check. If you can see from BB, there's no profitable deviation for the role player nor the column player. So this is the unique pure strategy profile. And for the second game, the unique Nash equilibrium is a mixed one in which the role player mixes 2/3, 1/3 between strategies A and B, and the column player mixes theta over 1 plus theta, 1 over 1 plus theta. So we're going to consider convergence of pure strategy profiles generated by a particular form of dynamics, better response dynamics. And I'll define it in a bit what it is, but essentially what it is at any strategy profile or at any time step, a player is chosen at random and updates its strategy unilaterally to one that yields a higher payoff. Okay? And if we apply this form of dynamics to these two games, we see that for G hat, the sequence converges to the Nash equilibrium BB, the unique pure Nash equilibrium, whereas in G, the sequence, pure strategy sequence, follows the better response cycle, AA, BA, BB, AB, with equal frequency. So it's not contained in any pure epsilon equilibrium set for epsilon less than 2. This being because this strategy profile is visited infinitely often, and always there's a deviation of value 2 from that strategy profile. So this is an example which shows that closed games need not have similar limiting dynamics and similar in terms of being contained in epsilon equilibrium sets. I showed that for a simple dynamics, better response dynamics. You can also look at fictitious play. Same phenomenon happens. Games that are closed need not have similar limiting dynamics. So that was the motivation for our paper. The question that sort of we wanted to answer was, can we identify classes of games in which convergence behavior of adaptive dynamics is robust to small perturbations or misspecification of payoffs in the sense of guaranteeing convergence to small approximate equilibrium sets. And one class that comes immediately to mind is potential games. It is well known that for finite potential games, many reasonable adaptive dynamics, including best response, better response, fictitious play, and even Logit in some sense, converge to a Nash equilibrium. So the question then is, does this convergence behavior extend to near potential games, games that are close to the set of potential games? And relatedly, so if we're given a strategic form game, can we find a near potential game and use the distance between the two to obtain a quantitative measure of the size of the limiting approximate equilibrium sets? So our contributions are as follows. We will study convergence properties of dynamics by in general strategic form finite games by exploiting their relation to closed potential games. Our approach will rely on using the potential function of the closed potential game in the analysis of dynamics. We will show that for a given game, we can find the closest potential game by solving a convex optimization problem, enabling us to give this distance that I told you about. And we will show that many reasonable adaptive dynamics converge to approximate equilibrium sets set where the size of this set is a function of the distance from a closed potential game. And the immediate implication is that if the game is near potential, then we will obtain convergence to a small approximate equilibrium set. More specifically, in this talk especially, I will focus on 3 commonly studied update rules and establish the following results. I will look at first discrete time better response dynamics and show that the sequence of pure strategy profiles generated by this dynamics converges to a pure epsilon equilibrium set. Here, epsilon will be proportional to the distance to the set of potential games. I will then look at discrete time fictitious play dynamics and then show that the sequence of empirical frequencies converges. This is actually a stronger notion of convergence, converges to a neighborhood of a mixed equilibrium. This is true for near potential games only. I will elaborate on this result when we come to that. And here again, the size of the neighborhood increases with the distance, so it's also proportional to the distance to a given game. And similarly, probably I won't have time to come to Logit-Response, but you can also show that the stochastically stable strategy profiles under Logit-Response Dynamics are also pure epsilon equilibria. Again, epsilon is proportional to the distance from the set of potential games. So let me start with some preliminaries to set our notation and terminology. I'll be focusing on finite strategic form games represented by this 3-tuple. M here is the set of players. EM is the set of strategies. As usual, the product set here, E, is the set of strategy profiles, joint strategy profiles. UM is the payoff function for player M, which is a mapping from E to R. It's a real values function. Our notation is strategy profiles. Pure strategy profiles we're going to denote by P. And P minus M is, as usual, the strategies of all the other players other than M. Delta EM will denote the set of probability distributions on EM. And elements of that are mixed strategies for player M. And we will call a collection of mixed strategies a mixed strategy profile. And the notion we're going to be interested in is this epsilon Nash equilibrium. And we're going to say that a mixed strategy profile is a mixed epsilon Nash equilibrium. I will drop Nash most of the times. If unilateral deviations cannot improve payoff by more than epsilon. Okay, so we may have a little bit of improvement, but not more than epsilon. So we're just introducing a little bit of slack with respect to Nash equilibrium to capture the notion of approximate equilibrium sets. So if epsilon is 0, obviously this is just a mixed Nash equilibrium. And moreover, we're also going to be interested in pure epsilon equilibria, and those will be if xm is degenerate for all m, meaning it assigns probability 1 to the pure strategy profiles, then we're going to refer to that as a pure equilibrium, or with the same notation as a pure epsilon equilibrium. Okay? So another important notion will be the notion of exact potential games. We say that a game G is an exact potential game if there exists a function phi such that the payoff difference from unilateral deviations for all players is given by the difference in the value of this potential function. The key point here is that this is true for all m. So you can view this potential function as, in some sense, aggregating the preferences of the different users or agents in the sense that if you have the potential, maximization with respect to subcomponents coincide with the individual maximization problem of the players. So another important result will be from Monder and Shapley, and to introduce that result, I need one more notion. I will use the notion of a simple closed path. This is Monder and Shapley's terminology. I don't know why they use simple, it's just a path. It's basically pi and pi plus 1 differ in the strategy of only one player, and it's closed, or it's a cycle. P0 is equal to Pn. Okay? So you consider these cycles of pure strategy profiles, and you consider the total utility improvement along that cycle. And there's this very beautiful characterization of an exact potential game, which is a game is a potential game if and only if the total improvement along any of these cycles is equal to 0, which makes sense, right? Because in these improvement cycles, utilities keep changing, and there's this potential function that can trace that change. So if it's a closed cycle, you will end up in the point that you started from, so it has to be equal to 0. So this will be just relevant in one of the results that we have. So before I sort of dive into the analysis of the dynamics, let me define the notion of the distance that we use. So we adopt the following metric to measure the distance between games. So if you have G and G hat, two games with the same set of players, same set of strategy profiles, different utility functions. We say that the maximal pairwise difference, or MPD, between these games is the maximum over all players and over all strategies that differ in only the strategy of player M. The differences of the utility improvements. Okay, this is a little weird notion when you first see it, because in general, when we think about defining a distance notion between games, one can say, well, why not define the difference of the utilities, maximum difference of the utilities as the distance? We choose to work with the utility changes or improvements rather than difference of utility values, since the form is a better representation of strategic similarities. And what do I mean by that? Think about a game. Generate another game by adding a constant, 1, to each of the payoffs. So if you think about utility values as your distance, these two games differ by that constant, by 1. However, if you look at this equilibrium set or properties of dynamics, best response behavior, that doesn't change, because best response behavior or equilibrium depends on the difference between utility values, utility differences. So it's the utility differences that determine such properties. So therefore, we actually work with these utility differences in terms of defining the distance. So this notion of strategic similarities we have actually worked on in more detail in our other papers. So if you're interested, it would be good to take a look at that. But from now on, I'll just not, mention anything else about the strategic similarities. Just I will use MPD as a notion of distance between two games. And I will refer to games with a small MPD to a potential game as a near potential game. So how do we, yes? Mm-hmm. Yeah. So normalizations just get out of the picture by this definition. Normalize the utility difference? Normalize the original game, you mean? Uh-huh. Yes, exactly. So the point I'm trying to make is when you normalize, the equilibrium doesn't change. So I can normalize it and then use the equilibrium, use the utility difference as my metric. Okay? So the first question that comes to mind, and it's not too hard to answer, is I'm given a game. I would like to find the closest potential game, closest in the sense of this distance notion. How do we find that? So let's try to write down an optimization formulation for that. And the key point to realize here is that potential games are characterized by linear equality constraints. So if I'm given a game with utility functions um, the closest potential game with utility functions u hat m can be obtained by solving the following convex optimization problem. So minimize the MPD over the potential function phi and the utilities u hat subject to the exact potential condition. Okay? And why is this a convex optimization problem? Well, this part is linear in phi and u hat, which are the variables, decision variables.
By using u hat, just plug in phi.
Yeah, just.
U hat here. Instead of u hat, write phi.
That's fine. I'm just trying to make it more sort of apparent here. But this is a linear constraint, and sort of a little bit thought goes into establishing that this is a convex function. And this is actually a convex function. Why? Because it's the maximum of, you can put phi and eliminate u hat if you wish. I think I wrote it this way because we also consider projections onto ordinal or weighted potential games. Although for this talk I'm only going to be focusing on exact potential games. Anyway, so this is actually a convex objective function. Why? Because it's the maximum over finitely many linear functions. So if you think about finitely many linear functions, take the maximum, that's nothing but a piecewise linear convex objective function. So it turns out to be, we can obtain this distance or the closest potential game using a convex optimization problem. And as I mentioned, if you're interested in thinking about other norms or actually projecting onto other nice classes, I didn't talk about this, but ordinal or weighted potential games, one can also do similar things, although now at that point the problem will not be convex, because even weighted potentials or ordinal potentials sets is not a convex set. But one can actually think about doing approximations, and that's what we did in this other paper. Anyway, from this point onward, I'm not going to refer to this problem. I'm just going to say, if I'm given a general game, there is a means I can find the distance to the set of exact potential games. And from this point onward, I'm going to analyze behavior of adaptive dynamics and try to use the distance to provide bounds on the limiting sets of this adaptive dynamics. Let me start with discrete time-better response dynamics. So how does that work? So at each time step t, we choose a single player at random. And this random could be really anything, except that we want a probability distribution that has full support over the set of players. So each of the players have positive probability of being picked at each point in time. Suppose player M is chosen, R is the current strategy profile. Then player M updates its strategy to a strategy which yields a strictly better payoff. Okay? And if there are more than one elements of this set, you choose any one of them uniformly at random. Okay? So very simple. At each point in time, player looks at his better response and moves if there's a strictly better response. So I will consider convergence of the sequence of pure strategy profiles, and I will refer to that as the trajectory of the dynamics. It is well known that in finite potential games, trajectories converge to a Nash equilibrium, and this is just established using the fact that the potential keeps strictly increasing. You have finitely many strategy profiles, potential is bounded from above, so you will hit the maximum potential, which is a Nash equilibrium, pure Nash equilibrium. So how do we analyze it for near potential games? Or our result for near potential games is as follows. If you have two games, I'm saying near potential. Actually, the result is true for general games, but because the size is a function of the distance, it will only make sense for near potential games. Okay? So consider a game G, and let G hat be a close potential game with distance equal to delta. Okay? In G, if you apply discrete better response dynamics in the original game, then the trajectory is contained in the pure epsilon equilibrium set after finite time with probability 1, where that epsilon is equal to delta times E, as cardinality of this set of strategy profiles, pure strategy profiles. Okay. How does the proof work? Just to give an idea. Well, we use a very natural Markov chain representation for the analysis of this finite game. So we map each of the strategy profiles to a state, so that yields a finite Markov chain. And there will be a transition between the states if R and Q differ in the strategy of a single player, and QM is a strictly better response for player M. And the transition probability will be basically given by the probability that that player is picked times probability that he actually picks that particular strict better reply. Okay? So that's just the Markov chain representation for the trajectories, for the evolution of the trajectories. Now, this is a finite Markov chain. With probability 1, we're going to hit a recurrence class. So the question is, in this recurrent class, how much can the payoffs change when the trajectory jumps from strategy profile to strategy profile? So in order to put a bound on that, we consider any transition between the two states in the same recurrence class, let's say from P to R. So for any such transition, it's the same recurrence class. So if I go from P to R, in finite time, I will go back to P. So that creates a cycle, right? And using the zero total utility improvement property of potential games, and the fact that our original game is delta close to this potential game, I can actually write down the utility change I will incur around this cycle, and that gives me my bound on the epsilon here, and the epsilon equilibrium set here. Okay? So is the idea clear? Essentially what I'm doing is just using the total utility improvement property of potential games, and I put this perturbation, or the fact that the game I'm analyzing is delta different from this game, and then when I add the two, that gives me that the payoffs cannot change by more than delta epsilon. Okay? So, so that's for discrete time better response dynamics. Let me next look at fictitious play. which is a much more interesting or much more involved dynamics. Essentially, the idea of fictitious play is the following. Again, similar to before, each player keeps updating their strategies in discrete time. And what each player does is, he assumes that each of the other players is using a time-independent stationary mixed strategy. This is incorrect, but that's the assumption of fictitious play. And for that mixed strategy, he forms some predictions using the entire history of the play. In particular, he forecasts that the other players' strategies are independent empirical frequency distributions. Okay? And in more detail, we can write down these empirical frequencies. Let this 1 be the indicator function, which will be equal to 1 if PTM is equal to PM and 0 otherwise. The empirical frequency at time t of strategy QM is nothing but the fraction of times the player used QM up to time t. Okay, so that's this fraction. And if you put all these frequencies into one vector for each of the strategies of player M, that will be the empirical frequency distribution, or I will also refer to it as a vector of player M at time t. And at each time instant, given the empirical frequency distributions, each player essentially is myopically plays a pure best response against that empirical frequency distribution. So it is known that empirical frequency distributions converge to the mixed equilibrium set in potential games. This is a result by Monderer and Shapley from their '96 paper. We're going to next analyze this dynamics for perturbations of potential games. So a key idea in the analysis will be the following, or one of the key ideas. If you observe more carefully the evolution of the fictitious play, the joint empirical frequency vector actually evolves as follows. So mu t plus 1 is equal to the previous frequency vector mu t, a convex combination of the previous strategy profile mu t and this it. And it is nothing but a vector which has a 1 at the strategy that's played at that point and zeros elsewhere. Okay? So we're basically taking mu t, correcting for the time factor for mu t, and adding the strategy that's played at time t. Okay? So given this, we can actually see that mu t plus 1 minus mu t, the difference between two consecutive strategy profiles, is given by 1 over t plus 1 times the norm of it minus mu t. Both of these guys are bounded. This is bounded by 1, 0, 0. So this is a probability vector. So essentially, this says that the difference between them is order 1 over t. As t goes large, the change in the empirical frequency vector mu t is small. And that's an important fact. The fact that the step size is 1 over t in changing the empirical frequencies is what enables us to establish convergence. So, okay, how do we analyze fictitious play? Especially even if you're at a potential game, the first thing that comes to mind is, of course, use the potential function. And that's what we're going to do even for near potential games. M is the number of players, and what we can establish is that if G is a game, G hat is a near potential game with potential function phi, and the distance is delta, then if at time t, empirical frequency vector mu t is outside an epsilon equilibrium set of G, then this potential actually increases by a certain amount. Increases for large t, but essentially the difference between them is lower bounded by epsilon minus m delta divided by t plus 1 plus order 1 over t squared. Okay? So let me first talk about the implication and then show you how to prove this. Well, this says that if mu t is not in an epsilon equilibrium set for some epsilon greater than m delta, and t is sufficiently large so that we can actually cancel the impact of this term out, then the potential evaluated at empirical frequencies will keep increasing. Again, this is a finite game. Potential should be bounded from above, so it cannot do this infinitely often. So the empirical frequency vector eventually reaches the epsilon equilibrium set. Okay? So I'm not saying it converges yet. I'm just saying that from this potential increase, what we can see is that it will actually reach the epsilon equilibrium set. It may leave, but it will again come back. Okay? The question is, with this oscillatory behavior, how can we say something about its convergence behavior? Okay. So let me skip the proof of this part. Essentially, it uses a Taylor expansion of phi and uses the multilinear nature of phi as well as the properties of fictitious play to show this increase in the potential function. But come to basically a better sort of more interesting part where we use the structure of the game a little more to establish convergence. So the implication, as I tried to explain, of the previous result is that if you have a game G and close to a potential game, then the empirical frequency vector of the fictitious play will converge to this set, which is basically a set of mixed strategies with potential greater than or equal to the minimum potential in that epsilon equilibrium set. So what does this say? Well, it will eventually reach epsilon equilibrium set. Whenever it's outside epsilon equilibrium set, potential keeps increasing. So it will actually converge to a level set of the potential, and that value of the level set is actually the minimum value over this epsilon equilibrium set of the potential. I didn't say it very well. So it reaches the epsilon equilibrium setup, so the potential will be larger than the minimum value there. When it's outside, it keeps increasing, so it will never fall below that minimum value. Okay, so this is establishing convergence to a level set. So let's then specialize this result to a potential game, delta equal to 0. And this theorem implies convergence to this. A set with potential greater than or equal to the minimum of the equilibria potentials. So if you have a unique equilibrium in the game, this establishes convergence to an equilibrium. But if you have multiple equilibria, this only says that we converge to a set whose potential value is larger than the minimum of the potentials of different equilibria. While this set contains the equilibrium set, it may have many other mixed strategies as well. So there is a gap in this result with respect to Monder and Shapley. So we try to resolve that by trying to understand the structure of epsilon equilibria set a little better. And here is the observation. If you have a game with finitely many equilibria, for small epsilon, epsilon equilibrium sets are contained in disjoint neighborhoods of equilibria. Okay? So the example is the classical battle of the sexes, which has 3 equilibria, 2 pure, OO, FF, as well as 1 mixing 0.6, 0.4, symmetric equilibrium. And the picture is as follows. When you change epsilon from 0.2, 0.3 to 0.4, these are how the epsilon equilibrium sets look like. So for small epsilon, they are contained in these disjoint neighborhoods. So what's an implication? Well, why is this true? First, this is basically coming from the upper semi-continuity of the equilibrium correspondence. How much time do I have? 4 minutes. So let me skip this if you can. I was going to explain this, but if you can take for granted that this is true. It's really, the equilibrium exhibit very weird behavior because the equilibrium correspondence only has this upper semi-continuity property. It's not continuous, but upper semi-continuity enables us to establish that for small epsilon, epsilon equilibria sets are contained in disjoint neighborhoods of the equilibrium. So how do I use that? Well, so now, if for small epsilon, essentially what this says is I can just concentrate on different disjoint neighborhoods of equilibria. And so think about this as our epsilon equilibrium set, I can actually fit a ball around this equilibrium with size f of alpha, and that each ball that I fit around equilibria will be disjoint from each other. Okay, so this is very key, I think, in the next result. Using this property, we establish our main result for near potential games. In particular, if G has finitely many equilibria, there exists some delta bar such that if delta is less than delta bar, if our game is close to a potential game, then the empirical frequency vector converges to a neighborhood of the equilibrium set, and the neighborhood size is given by this quantity here. I did not go over F very well, but F is basically the size of the ball that I fit around my equilibrium set. And let's look at the extreme case now. This is true for any epsilon between 0 and epsilon bar. So if I look at the extreme case, G is a potential game, delta equal to 0. Delta equals 0, f of 0 is 0, so this term drops out. And if I take epsilon to 0, f of epsilon goes to 0, then this essentially recovers Monder-Shapley result that we converge to a mixed equilibrium set. Let me quickly, 1 minute. Let me quickly tell you the main ingredients of the proof. It consists of 3 steps. The first step is basically providing a lower bound on the increase in the potential function outside an approximate equilibrium set and showing that it's actually proportional to the length of the path traveled outside this set. Okay? So if you have a mu t leaving some epsilon, m delta plus epsilon equilibrium set, from our previous result, the potential increase is lower bounded by epsilon over 2t for large t. And because mu t plus 1 minus mu t, remember that was small enough, for large t, the difference between the empirical frequencies was small enough, we can actually provide a lower bound in terms of this distance between the strategy profiles. Using this, the next thing actually establishes the key point that the trajectory cannot keep on going between different neighborhoods of equilibria. It can visit the neighborhood of an equilibria infinitely often around only one equilibrium. Okay? So essentially it says it will stay close to only one of the equilibria. Given this, we can then establish, okay, it will stay close to this one particular equilibrium. How much can it escape from the epsilon equilibrium set? And we can establish that, I'll skip the details, but it can escape at most this much. Okay? And essentially that establishes our result. We are putting a ball around the epsilon equilibrium set, and from that ball it can at most escape d, which is this value. So we're staying within that neighborhood of equilibrium. So as I suspected, I wasn't able to come to Logit-Response, but let me skip that. Logit-Response also has nice properties in terms of near potential games. Essentially, we can obtain bounds on the distributions. I didn't explain the distributions, but essentially the limiting behavior of this dynamics was also epsilon equilibria of the original game. So let me then conclude. We presented a framework for studying behavior, convergence behavior of adaptive dynamics in general games. We provided bounds on the limiting behavior, and these bounds, of course, are informative if we're thinking about games which are close to the set of potential games. I only focused on discrete time update rules. The paper contains also continuous time update rules and others. And the future directions is essentially this was started by saying, can we find some nice classes of games for which we know the convergence is nice? So maybe around that set, we also have some nice convergence. So this will allow us to study convergence for a larger class of games. The next step is maybe we can also look at supermodular games or zero-sum games and see if perturbations also preserve dynamic properties. Another point that we're very interested in is, now that we have an good understanding of these dynamics, can we think about maybe designing incentive mechanisms for these near potential games to steer behavior toward nice property or equilibria with nice properties in terms of maybe welfare functions. And finally, this is also something that I'm very interested in. What we characterize this convergence behavior for perturbations of potential games. One can also ask a very natural questions in this context of adaptive dynamics. Why are we assuming that all the players are using the exact same update rule? Can we think about each of them maybe is perturbed? Maybe they're using some slightly different update rules. Can we analyze such dynamics? So that's another question that we're very interested in. And that concludes the talk. Thank you.